So hello, welcome to our Keeping It Real, DevOps, Containers, and Cloud at OpenStack, or at NetApp. My name is David Blackwell. I'm a technical marketing engineer at NetApp. I cover OpenStack and configuration management. Joining me in a bit will be Pete Bray. As you can see, he's our product marketing manager for OpenStack. Together, we have over 40 years of experience in IT, which is kind of nice to be able to say. So what we're going to be talking about today is how NetApp uses all of these technologies for ourselves. And I actually had someone come up to our booth and ask if NetApp just sells stuff or if we actually use it ourselves in our environment. So I was actually happy to not only have an answer for that, but have this session. So I'm trying to make this session not a huge marketing sales thing, just to let you understand how we consume and what we have learned about OpenStack as we've gone along. I will say, though, also, I want to remind you, don't leave early for the session, because you all should have a blue raffle ticket, and we're raffling off a wireless folio at the end. For those of you who don't know 100% what NetApp's involvement is with OpenStack, we're the largest, based on the first OpenStack Summit in 2017, we're the largest commercial vendor providing storage for OpenStack. 5 out of 7 enterprise deployments of OpenStack use NetApp in some form or fashion. We are the largest contributor to the Manila project and a massive contributor to the Cinder project, and both PTLs, previous PTLs, work at NetApp currently. We originated the Manila project and helped drive a lot of the newest features that project comes out with. So NetApp's OpenStack journey for ourselves started in 2014. We had been doing all VMware and Hyper-V up until that point. Part of the problem with that is expensive to do all VMware and Hyper-V. That's one of the advantages of OpenStack, is it's quite a bit less expensive than the alternatives. But when you've never done it before, scaling up to a massive use case is very difficult. So what we did when we first started is we did individual all-in-one nodes. We call that version 0 because it was terrible. Version 0 was, again, all-in-one nodes. They're difficult to manage. There's too much sprawl as you're trying to have a more focused management interface. Having to have each individual node be its own region and location as we set that up just didn't work. We eventually were able to move on to Puppet automation and our non-disruptive upgrades. At Kilo is where we really started having a better layout and use function. And I'm going to show you in a few slides what we made that look like, what we learned from our first releases, and how we've made changes. So some history around the cloud environment I'm going to talk to you about. We call it our Engineering Shared Infrastructure Services, ESIS. So we have 5 major physical regions that we run OpenStack in for this team. Each location is a region, except for the North Carolina one. There's actually 2 regions there. So it's actually 6 extra regions now. It is 9 total labs in 5 locations, and there's over 5,500 users who access and utilize services provided by these region labs. Also, our entire OpenStack engineering environment is supported by only 8 people. So 8 people are responsible for the entire world's upgrades and distributions and region expansions, troubleshooting, everything. So we have an excellent team that's very excited about OpenStack. Most of them have spoken at summits in the past, so if you've been to more than one summit and enjoy NetApp information, odds are you've seen some of them. We call our engineering group Customer Zero because they're the first person to have to work with something. Who's ever encountered a bug in software? So everyone has. It's impossible to write really complex software and not have bugs. Our flagship product, ONTAP, is 25 million lines of code. That's a lot of lines of code. There's going to be bugs. So anything that we develop ourselves not only is used by us, but is tested first with engineering. That's our Customer Zero. We want to be able to eliminate any challenges that our partners and our customers are going to have, as well as spot and fix anything that might have gotten past our own QA processes during development. It's also necessary because of the massively distributed area that our environment's over, is to be able to deliver all our services seamlessly. If there's any kind of an interaction that causes problems, it's going to show up in Customer Zero. Something else that's very interesting about how Customer Zero is actually used by our end users is they don't know or care what hyperscaler they're on, or sorry, what hypervisor they're on. We use a web portal. They go to it, they acknowledge, they mention what they need to test, how long they need to test it for, what kind of build they need, and then automated service goes out, finds our AZs that have the least amount of load or the most amount of resources, or match their requirements, and then bring up the instances, and they simply get an email. Your VM is ready. This is the IP address to use for it. This is your login information or the key you have to use to access it. Because our engineering lab is entirely internal only, it doesn't have access from the outside world in, we use 100% provider networks within Neutron. So we don't have to use any floating IP addresses. So as a system's built, its IP address is its accessibility point. Just some statistics about our current setup. We have the capacity right now across our 3 VM platforms, again, Hyper-V, VMware, and OpenStack, to run 75,000 VMs. Our OpenStack capacity is 20,000 VMs, and we have a little over 9,000 VMs actively running today in OpenStack. My 33 numbers are a little off. It's closer to 30% for KVM, 15% for Hyper-V, and all the rest is VMware today. But versus 2 years ago, when it was 15%, 45%, and 40%, OpenStack is making a huge advance in our internal use cases, again, because we're wanting to cut back on those licensing costs with our other options. Additionally, we had originally thought that 80% of our base would be hit on OpenStack KVM by the end of this year, but it looks like it's going to take a little bit into next year, but it's still where we're going towards, that the majority of our engineering work will be done entirely within OpenStack. So what defines our OpenStack deployment? We use FlexPod. FlexPod is nothing but a converged infrastructure term. It's Cisco Nexus switches, Cisco UCS, and NetApp storage. We use the OpenStack RDO distribution, and we are currently running Newton. From Kilo through Newton, we have run every single upgrade. The reason we haven't gone from Newton to Otaka or Pike or Queens is because we're planning our 3rd iteration of our OpenStack lab, and we're going to make the jump just to Queens when we do that. Currently, we do deployments via Puppet to manage our upgrades and our deployments. We use Jenkins and Git to store the tests we need to run for when we push a new deployment to verify that there's no issues with it. So this is what our version 1 architecture looked like. So when we realized that OpenStack was going to be accepted and more than just a use case test. We needed to go to something that was far more expandable and robust. So originally, we started with a multi-region approach. So region 0 was Keystone and Horizon, as well as the Galera database, MySQL database clustering that we would use. And then every individual rack was its own region. So a region consisted of 16 nodes, 1 controller node and 15 compute nodes. When we reached the limit on that, we would deploy another region right next to it that was, again, the same way. This is not a good architecture to use, and we'll show you where we switched from that. But we gave each region its own Nova and Neutron networks. The advantages to this was within the region, we could easily migrate VMs between the Nova compute nodes for upgrade purposes. But if a massive deployment had to be done and it had to span regions, we couldn't span the VLANs across all of those because they were individual Neutron environments. Each region also received its own independent Nova and Cinder storage. So again, that wasn't able to be shifted between regions to upgrade that. So our biggest pain points that we came across in this, RabbitMQ really got overloaded in each region. It gets hammered pretty hard, and by having that structured within a single controller in each region, that caused us a major problem. The inability to do live migrations between regions also caused us a lot of headache and difficulty, as if an entire region went down, if someone tripped and pulled down a rack, everything had to be force migrated, or if we knew we were moving a rack, we still had to power everyone's VM off. We had to do the back-end work to move all the metadata from one region to another and then bring the systems back up. And again, I mentioned it a little earlier, but because of the inability for VLANs to span between regions, it made some massive projects very difficult to have a way to deploy and communicate to each other. So from those pain points, we moved on to our version 2 architecture. And this is what we are currently running today, but we are going to be switching it soon. So the version 2 architecture, region 0 is just Keystone. We've actually separated Keystone and Horizon from each other in order to have fewer points of contention. We also have, it's not really a region, just its own cluster grouping that is our Galera cluster and our Ceilometer cluster. So those have actually been extracted from each individual region and from Keystone. So that's in a clustered environment that's accessed via load balancers outside of the nodes that run any of the OpenStack services. We now run on single regions per location. A region is 3 controllers in a load balance setup that also allows RabbitMQ to be clustered across the 3 nodes. So as load balancing comes in, whichever node the load balancer sends it to, that's where the requests and the information is requested from and put at, so the load on RabbitMQ is distributed and doesn't have that single pain point. Beneath that setup, what we do now is availability zones. So before, where every rack was its own region, now every 2 racks is an availability zone. So availability zones are entirely compute. This allows us to better migrate between availability zones live as we need to control that. It allows us, by again putting the controller as a load balance cluster, allows us to manage the services better as they're coming in. And then a compute farm now, since it's 2 racks of full compute nodes, went from 15 compute per collection to 45 compute nodes per collection. This also allows us to run DHCP at the neutron level. The old version, we actually had to write our own utility that extrapolated DHCP from our actual system, made individual requests, and passed them in. It was painful and clunky and caused more problems than it solved, but it was the only way we could do it across our multiple region approach. So our biggest differences between these architectures that I want to point out, we moved Newton to the top level of, we moved Neutron to the top level of management within the clustered control as opposed to a level down so that it now handles DHCP. We also now are using all cloud init images. I wasn't there when they decided not to use those originally, so I'm not sure why that was, but now of course we can do injected key pairs, so that's a faster distribution. Availability zones versus regions is probably the largest change. What we do today, because of suggestions from Cisco and Red Hat, and we haven't hit this count yet, but if we hit 400 compute nodes in a single region, we will stand up a second region in the same physical location. We've just been told that the load on RabbitMQ and the load on Keystone in your database at that point just becomes larger than it can handle. However, as the cost of compute nodes come down and how much RAM they have and how much processors they have go up, that number is actually getting smaller. A year ago, our default presentation was 2 CPUs and 6 gigs of RAM, and now a default bare minimum presentation is 4 CPUs and 8 gigs of RAM. So we're actually going to be lowering that number from 400 compute nodes to 200 compute nodes, only because an individual compute node can now handle a much higher density of instances. What we're also going to be doing, we haven't done it yet, but we're going to be splitting RabbitMQ off into its own region to be able to further split out how much load that sticks with. But because of the nice region and availability zone setup we do, it's very easy for us to scale across regions. Everything in our system, every node, is still part of a UCS farm. And so everything is LUN booted. So we have our generic OpenStack configurations that we've made LUN images of. And when we have to stand up a new region, we snap mirror those LUNs using NetApp backend storage, snap mirror from the originating region to a new region, add those as mountable LUNs and bootable LUNs for those nodes, and just bring the region up. It takes us today to get an entire region stood up, and into production takes us less than 90 minutes. So now I want to talk a little bit about where we're going in the future and what we've learned from this. And I'm going to actually talk a little bit more about this even in a session that's after this one, is we're going to switch to containerizing OpenStack. We will be moving for multiple reasons in order to containerize to avoid library conflicts. That's a huge advantage of containerizations. And we are going to use the Cola Ansible project to do our deploys. We found that it's one of the more easy to use and feature developed but modifiable projects currently for deploying containerized OpenStack. This will also mean we'll be switching to Ansible for configuration management from Puppet. And we're going to go with the jump directly to Queens. Also, every new release that comes out, we will be running every release cycle upgrade because the containerization and Ansible projects allow for an incredibly easy upgrade, as well as if you do, God forbid, run into a problem during an upgrade, the containerized OpenStack actually allows, to a point, downgrading without a lot of issues. We're going to be running IPv4 and IPv6 in our environments. Our controller nodes will be running IPv4 for the OpenStack backend network, but every one of our instances that we run will be IPv6 enabled and configured. Ceilometer is going to get its own RabbitMQ server, just again to take some of that load off that might be in the individual locations. And I'm going to hand it over now to my colleague Pete, who's going to be able to talk about what we do in Customer 1 with containers.
Thanks, David.
Thank you.
A great update on what we've been doing, eating our own dog food, so to speak, with OpenStack. And I'm going to shift gears a little bit. How many of you in the room have an interest in containers, deploying containers, using Kubernetes, OpenShift, Docker? Okay, a fair amount of you. Good. So I'm going to talk a little bit about our own use of container technology. It's primarily around Red Hat OpenShift, but we were facing some challenges. A decent-sized organization, 9,000 employees worldwide, lots of storage, lots of controllers to deal with, and dealing with that complexity. You can also see lots of applications, and some that have been deployed in a SaaS environment, and clearly that's the direction we want to continue going in the future. We're just facing a lot of problems in terms of the overall complexity, and so we're looking for a much simpler way to be able to handle this. As David talked about our Customer 0 program using OpenStack, we have a Customer 1 program, and this is actually with our corporate IT organization, where we are actively deploying container technology to help us deal with some of these problems. So our biggest top challenges were really having a scalable and consistent storage for all the applications that you saw on the previous screen. We also, and as David pointed out, using Puppet, but also moving more gradually towards Ansible for automation. So we wanted to have an environment that was much more automated than it was in the past. We also needed the flexibility and the speed of DevOps practices. And that's one of the things that we've been able to implement through the years. And finally, as I showed on that previous slide, moving more towards SaaS models, building applications that are supported by microservices was really a key attraction point for us. So we deployed Red Hat OpenShift, and one of the unique things that NetApp as a company brings to the table for containers is a project called Trident. Has anybody heard of Trident in the room? I see a few heads shaking, but Trident it's an open source product or open source project that NetApp actually led the development of and supports. And it's essentially an automated storage provisioner for Docker, Kubernetes, and OpenShift. What does that mean? It means that an application developer can issue a persistent volume claim, and automatically the backend storage is plugged in, the physical volume is plugged into the persistent volume claim. This eliminates a lot of overhead. It eliminates a lot of handoffs between the development teams and our storage administration teams. So it was really a big boon for them. Trident has actually been out, I think, several years now at this point. We have many, many different customers who are using it in addition to ourselves, and it's worked very well, and it's helped solve a lot of the pain around storage provisioning for container environments. Architecturally, some of the things that we wanted to achieve was supporting both our OpenShift and Kubernetes environments, being able to meet our persistent volume demands, as well as provide that dynamic storage volume provisioning across all of our portfolio of products. So whether it's an ONTAP system, our SolidFire system, our E-Series systems, we're able to do that. And in the end, it helped us lower our total cost of ownership by automating the storage provisioning process. So it was really a big boon for our development and our infrastructure teams. It also helped us standardize our architecture, and it reduced one of the big problems that we had is applications that were decommissioned a lot of times, and I'm sure a lot of you run into this problem, where the storage volume that was supporting that application is still there. And within Trident, there's the ability that once a an application has been decommissioned, the volumes that were associated with that can also be reclaimed. So there's some pretty powerful features with Trident. Some of our learnings and our results by deploying this architecture for our application development environments is it enabled us the ability to introduce platform as a service with push button deployment using either NAS or block storage. It also enabled us better storage management so that we can actually keep track of our volumes and our usage and manage it much more closely. And it was also one of the final steps as we, much like many people are, moving towards a hybrid cloud architecture. We have applications that are public cloud-based. We have a lot of private cloud-based applications, and this architecture helped us in making that migration. Some of the biggest things that we learned in going through this process, though, too, is that you've really got to look at the environment holistically, and that's been a challenge for us as a fairly large enterprise, being able to get a handle on where all the storage resources are, what resources are being requested by app developers, and how do we get a good handle on that. Initially, when we rolled this out, it was a challenge to be able to troubleshoot and to identify and root cause problems. But once we worked through a lot of that initial deployment issues, we were able to get to a steady state environment that actually works very well for us and contributed to the total cost of ownership reduction that I mentioned earlier. And as I mentioned also, the reduction in handoffs and the reduction in tickets that were going back and forth between the developers and our operations team, that was also a big boon. So overall, it was really a great experience for us. That completes the presentation that David and I wanted to talk to you about today. I want to do a couple of things. First of all, I want to remind you that we have more sessions. I think we have some later today and tomorrow also, so please do come out and see our sessions. We also have a booth number B2, down in the Marketplace Expo, so come and see us there. At that, I'd like to open it up for questions. There are 2 microphones in the aisle, so please use the microphones if you want to ask a question. And then in a minute, we'll do the drawing for the bamboo pad. Any questions? And David, can you come up and help with questions also? Yes.
Hi, so you mentioned that you were planning to do upgrade to Queens. Can you talk about what process you're going to be doing for that? Is it just a lateral shift, or are you going to do an in-place upgrade?
It's going to be a lateral shift. We're going to be doing a brand new deployment in our version 3, and then we'll be either redeploying instances or packaging and moving them using other options.
Okay, thanks.
Absolutely.
Thank you.
With your OpenShift environment, are you running it on OpenStack, or it's a different deployment?
Today, most of our Kubernetes nodes run on VMware. Only because that's the team that won.
So then the follow-up question. I understand that you want to run Trident, but with VMware you can use their own Kubernetes provisioner, right? Assuming you use VMDKs and stuff like that. Can you compare about that?
The problem with that, though, is there's first of all, there's the performance hit of the VMDK connections. And then there's also the requirement that those have to be virtualized. Trident works with virtualized systems or bare metal systems and has actual communication connections to the protocols on the back end. So you issue your persistent volume claim, and it will actually create the volume and do the NFS mounts to the worker nodes to have that connected through, or the iSCSI mounts to the worker nodes to have that connected through. So you don't have a connection to a data store and then a VMDK within that, and then the presentation out. It also makes it easier to back up, restore, or do individual file pulls.
Okay.
What's the reason for you guys moving from Puppet to Ansible?
Couple reasons. Probably the #1 reason is we're a huge Red Hat partner. like to be able to tell them, yes, we're using all your stuff. The other being is there's very few, if any, Puppet container projects that already exist. And so as we're moving to that, and the Cola Ansible project is the best one we found that's an open source and controlled. Well, we're going to stand up and tell you by supported OpenStack, but we use RDO ourselves. But that's the biggest reason. We've also found that the development cycle for if we need a custom module or time to live is far quicker with Ansible than with Puppet.
Okay. Any other questions? All right, the moment everybody's been waiting for. Will everybody get a blue ticket?
If you haven't, stand up because I'm kind of short. Everybody got a ticket?
Okay.
Okay, shake it up.
Okay.
Oh, I'm Vanna. Okay.
Yes. Read the magical number.
265-237.
There we go. We have a winner. Thank you, everybody. We appreciate your time today.
Yep. And if you come back in a few minutes, I'll be doing a session on the changes we're doing around Cola Ansible to make adding NetApp backends easier in that project.